So our research community is interested in how materials change their behavior and physical properties with extremes of pressure and temperature. And sometimes if you want to get something to very high pressures, millions of times atmospheric pressure, you could just kind of squeeze it like this. But every golfer knows how you compress things dynamically, and that's when you slap it with something hard. And what we're doing here is using the dipole laser to compress our material in a few billionths of a second, and therefore get extremely high pressures and temperatures, which we then X-ray with the XFEL pulses here. So we can get pressures and temperatures here by compressing with the laser that we can't get using the static compression technique. So we can simulate the center of a planet, millions of times atmospheric pressure, thousands of degree Kelvin. So we were looking at the melting of iron and iron alloys here last night. And we can just obtain extreme states here, and with the very short X-ray pulses from XFEL, it's perfectly timed with each other to interrogate that state, even though it only lasts a few billionths of a second. Well, there's a setup very similar to this at the LCLS XFEL in the US, but their laser, the equivalent of DiPOLE, will only fire every 3 minutes or every 6 minutes. DiPOLE was designed to fire at 10 hertz, 10 times a second, so we can take many, many more shots, and that was one of the key things we wanted to test in this first experiment. Could we take data at this rate? We didn't get to 10 hertz, but we did get to 1 hertz last night in the last 6 or 7 hours of the experiment. So we had kind of kind of 4 sub-projects below the main proposal. One was technical development, so could we get the 1 hertz system up and running and develop the number of targets needed. The iron group were looking at how iron and iron alloys that might exist in the center of the Earth behave, transform, melt under those conditions. The carbon group were trying to see how do various types of carbon, graphite, glassy carbon, transform into diamond. And then the final group were looking how do materials actually deform under these very short compression time, on these very short compression timescales, how do faults and things in the metal allow it to deform and twist and get to these high pressure states. That's always a good question to ask. So, if I were truthful looking at these individual experiments, it's fundamental knowledge of how materials change and things like this, but as a community as a whole, we're always looking to use extreme pressures and temperatures to make materials with properties that you cannot see at ambient conditions. Now the carbon group as we call them for the last week have been making diamond, which is not the stable phase of carbon under ambient conditions that we get on planet Earth, but they were looking how you could make diamonds from plastic in some extent. So it's a mixture of fundamental research to understand how material properties change under these extreme conditions, and then we can use that understanding to design materials that can only be made under these conditions.